Swayam Prabha. Digital India. Educated India.
Not necessary, I will just tell them. See, root locus is you get the, suppose you have this equation, okay. You get the homogeneous equation roots. The roots are minus zeta omega n plus minus, what is that, I, okay. This is the root. So, basically root locus is you take the real part, imaginary part, and real part put a point, imaginary that will come, okay. Now, you have some parameter in the system which is basically the mu, okay. For every mu you will have a value, and every gamma, that means mu and gamma is one combination. I gave 4 sets. For a given set of mu and gamma, sorry, not mu, that is what is that, omega RF. For omega RF and gamma with varying mu, you will get this and this, okay. So, you will plot those points. Mu will be varying, but the other two quantities are fixed. Then you go to the next set, that is all. You plot this in this curve, real and imaginary. Only thing is you have to estimate these two from your response curves, that is all, okay. Basically root locus is how the roots vary with any parameter, because this is a standard in control system or even in flight dynamics, because flight dynamics they will always want to see if I vary some parameter how my roots are, and you know that any root real part if it is on the right half, this is they call it S plane, okay, real and imaginary Laplace plane. So, if the root is on the right half, system is unstable, that is all. So, this is a standard root locus. Okay, now we will start with the blade equations, because you learnt about the basically the natural frequency, how it gets influenced by the hinge offset and the root spring, okay. Because the hinge offset and root spring they increase the flap frequency. When the flap frequency goes up, rotating flap frequency, then the hub moments go up and you get a more control moment at the fuselage. So, that is how the flap frequency dominates your design really. Flap frequency is very, very important, and you can have different types of rotor heads like articulated or hingeless, etc. Now, this is without any, I introduce the word coupling, only flap motion and pitch angle is set. But there are certain cases where they introduce coupling. Coupling means I will call it what type of coupling you introduce. Pitch, flap, then pitch lag and flap lag, that is structurally coupling by some structural design. Okay. I will put a structural design, though we do not call it like this. You can introduce these couplings. When I say pitch flap or flap pitch, when the blade flaps up, the pitch angle will change. Okay. This coupling is called they call it delta 3, alpha 3, something is there, they just call it delta 3. And similarly, when the blade goes back and forth, lead lag, again the pitch angle can change. So, this they call it delta 1. Okay. And of course, flap lag coupling is, there is no symbol attached to that, it is just a structural coupling, and how that comes I will explain. So, these are 3, and these couplings are very powerful couplings, in the sense they alter the dynamics of the blade, frequency wise as well as stability wise. So, we will, I will just briefly, this is not my, I will not be deriving a lot in these things, just to give you that these are very critical. Our flap equation is this, beta double dot, beta, some beta with respect to Lock number with the forward speed, and then there is a theta control input, which is independent of flap motion. The pilot gives that input. Okay. Suppose that input itself is a function of flap motion. Okay. That is, theta control is proportional to some factor to flap angle. Okay. Then what will happen? You may have pilot input plus another term which is proportional to the flap deformation. Now, the flap deformation term from here will be taken to the left hand side, because that will come as a beta. Okay. So, you find I can actually alter the stiffness term, because this is related to flap beta, which is a stiffness term. I can alter the stiffness term by introducing that pitch flap coupling. Okay. But since we have not introduced the lag dynamics, you can also alter the pitch of the blade by introducing lag pitch coupling. But how do you introduce the coupling is a question. Mechanically, or I would say the structurally, which I showed there, I will show a diagram now that will tell you how that coupling is. This is the pitch flap coupling. What is done is, you have the hinge, that is the flap hinge, okay, here. If the flap hinge is like this, look at only this diagram, this I will come to that later. Flap hinge is like this. Whenever flap motion means blade will come up and down, because this is the hub and it is the direction of rotation omega. But if the flap hinge is slightly inclined, now it can only flap about this hinge. The blade can only rotate about this hinge, okay, because it cannot rotate about it. Now, what you say is, I resolve this rotation Q into two components, So, q cos delta 3. So, I call it beta as q cos delta 3. Delta 3 is that angle, and then the other component which is pitching down, that is change in pitch angle, because the blade pitch angle is changing. That delta theta is q, because I put a minus sign because it is nose down, because when it is flapping up there is a nose down. So, your delta theta becomes equal minus q sin delta 3. Now, you replace q by beta. So, you will have minus beta sin delta 3 by cosine delta 3, which will be okay. So, please remember, whenever I call flap deflection is only about the hub plane, what it is coming out, that angle, not about what axis it is rotated. Okay. That is why I put flap beta, not in terms of q can be something else. I am replacing this q in terms of beta. Now, you see, whenever there is a blade is flapping, you have a change in the pitch angle. Now, depending on what direction this is, because it can be like this, it can be like this also. Okay. If it is like this, then when it flaps up, pitch angle will increase. So, that is why this is written as minus k p beta beta. This quantity is your pitch flap coupling. Okay. This quantity is coupling, but that minus sign is there. That is how you have arranged your the hinge. And you may ask, why should I put it? That we will come to that later. This is one type of arrangement. Another arrangement which is very obvious is this. Suppose I have a pitch horn. Pitch horn means pilot input comes to this point, it will come out of plane, and that means my pitch angle is changing. Okay. But once pilot has kept a particular pitch, the swash plate is held, and assume the control linkage is stiff. Then when it is flapping, flap hinge is here, okay, but this point cannot come out because it is held, which means it has to rotate about this axis, okay, because 2 points are held, and you introduce a delta 3 coupling. So, this happens automatically when your pitch horn kept in some place. So, in the design it is a little tricky. Suppose if you take this horn, instead of putting it here, you bring it up to this point and then connect it here like a 90 degree, okay, then it flaps, no problem. That is why if you see in most of the design, the pitch link, they will take it like this, bring it back to the axis, and from there the linkage will go. Then these 2 points are in the same axis, in the sense one horizontal, so it will do. Okay. Now, why do you do it is a question. Mathematically, what we said is this is the change in pitch angle. So, I have written here in the hover case from the flap equation, just change my theta control to theta control minus whatever is the change, delta theta, because delta theta is the change in the angle. Okay. So, you just put it and this delta theta goes there. If it is flap up, pitch down, this is flap up, pitch is down. Now what will happen? This term is flap up. When I put minus, what is it? This will become plus, right? So I should put a plus sign here. Okay. Because flap up beta is positive. That means pitch angle is reduced. Now you bring this term to the left hand side, add it with the flap term, and then substitute for delta theta as minus Kp beta beta. So when the minus, when it comes to the left hand side, it will become plus, because here this plus, if I put this directly, this will become minus Kp beta beta. So theta control becomes minus and take this minus to the left hand side, that will become plus, along with the aerodynamic terms, that gamma, because it will be theta has a coefficient. That coefficient term is basically aerodynamic term. That is, I will show that equation. See, all these terms, gamma over 2, entire term will come. Okay. In hover, mu will go off, only this term will remain. Okay. And that will go and get added to the already existing stiffness term. Okay. And I have written for the case of hover with mu 0, that coupling will be this term. You see, it is okay. I should put a plus sign here, because this is some because repeated use. Okay. This is the additional stiffness term which comes because of pitch flap coupling. If this is positive, please understand, positive pitch flap coupling means Kp beta is positive. That means flap up, pitch down. Okay. This is the convention, and then this is negative, means flap up, pitch up. Okay. Pitch up. So you always do not take this negative into consideration, only the Kp beta term as it is. If it flaps up, pitch angle will come down automatically. Okay. But it affects, please, the interesting part is it affects the stiffness term. In a simple quasi, I do not take the dynamics of the torsion here. I am just taking in a quasi study, change in pitch, if it gone up, okay, change, pitch angle is changed. Now you see, this is a aerodynamic term. So you have a stiffness even in hover. Forward flight, of course, you have mu, sin, psi, etc. is there. This gives additional stiffness to the blade in flap. But why do you want to have a additional stiffness to the blade? But you can make the flap frequency go very high. But earlier we said, if you make the flap frequency go very high, your control moment will become very large. So you do not introduce this in main rotors. Okay. You put this in tail rotor, because tail rotor loads are not much. Why you want to put a tail rotor? They do not want the blade to flap too much. Okay. If you make it stiff, the blade will not flap up. But imagine if you have to put a stiffness, that is going to become structurally very big, weight, etc. This is nothing to do with structure, just pure structural design, that coupling. So you introduce a coupling, I have increased my stiffness of the blade tremendously, and this if you see in tail rotor blades, in Cheetah Chetak it is there. Okay. Cheetah Chetak, I do not know whether you have seen it, you will go and see Cheetah Chetak, that those Alouette helicopter, they have this. Okay. That is because you do not want the blade to go too much, it is stiff and it will stay. But main rotor, you do not introduce this intentionally in articulated blades, but if you introduce, yes you can. But now you see, by changing the sign of this, I can increase my flap frequency or I can decrease my flap frequency. It can be less than 1 also. That is why I would say flap frequency is normally greater than 1, but it can be less than 1, depending on what coupling you have put in. So, usually people will say flap 1 point something, yes it is true, but there can be situations where you can introduce this coupling and influence the flap. So, that is why I said it increases flap stiffness, hence flap natural frequency, but you have to rotate in air because gamma is there. Suppose if there is no air, in vacuum means gamma is 0, because rho AC, because it is the ratio of aerodynamics to inertia. Okay. So, this is one coupling, but in hingeless blades and bearingless blade, this coupling always exists, you can't avoid, because of the elastic deformation of the blade they come, but you cannot quantify. It is a bit tricky, that is why they do not introduce this, but you solve a full elastic problem, elastic blade problem, because depending on the deformation you can have. Okay. It is like, suppose if this is the beam has, because it can have both flap and lag deformation. So, what will happen is the blade will bend like this. Now, any lift will give, lift force is acting on the blade, the pitch link is here, pitch bearing. If the lift increases, this will give a pitching moment with respect to how far I am back. Okay. Suppose if I increase the lag load, then how much I have flapped up, that much it will give the pitch. So, this is both flap and lag will introduce this coupling. So, when they actually made the elastic blade, this was one of the very important things they have to consider, because the deformation you introduce intentionally, you do actually unintentionally, I would put it, and that depends on what is the elastic deformation of the blade. Elastic deformation depends on what is the load. So, it is very tricky to say what exactly is the deformation you will get, the coupling, but one has to know that this effect occurs in those blades, because you may think that this is what the blade angle etc., but actually what you may get is maybe totally different in operation. That is why they do lot of world tower test, this test, several tests, and then check, match the data at least to a reasonable extent. Then they say okay, you fly. That is why these are all the pitch flap and pitch lag coupling. They did research essentially by experimentally, they made models and then studied the effect of these models, these parameters, what it does to the damping of the blade. This affects frequency, but this pitch lag coupling people do not introduce. Now you see pitch lag also you can give delta 1, lag is what, blade is here, you have a hinge like this, right. Now if this hinge is tilted like this, then when the blade goes, it has to rotate, you will get a change in pitch, but it is not introduced in blade intentionally, but they studied in experiments. It is very powerful in the sense in influencing the aeroelastic stability. Even though these tilts are, but how much angle? Now I will come to the delta 3. In the, they use 45 degrees. Okay. That means tan delta 3 is almost 1, right. So, tan 45 degree is 1. So, whatever, if it moves through 1 degree flap, 1 degree reduction in pitch. So, that 45 degrees they put. Okay. It is not a small 5 degrees, 10 degrees, it is substantially large. But the lag pitch coupling is very powerful. So, all these couplings are, they create, please understand, additional problems, additional effect into the dynamics of the blade. Now, I will, because pitch lag is similar, because there is nothing I can show, because we do not put that in this equation, because lag dynamics is not part of this, because this is only flap dynamics. Unless you introduce lag motion, you cannot add that coupling. But just for information I am saying there is another coupling which is called the lag coupling. Okay. Then you can have flap lag coupling. How do you get that flap lag coupling? See, one is from inertia, that is the Coriolis. As the blade goes up like this, you will get a Coriolis acceleration, that is from inertia. Okay. That is very powerful. In addition to that, structurally, can you have flap lag coupling? Okay. Show you that one diagram which you have seen earlier. This spring assembly, this is an approximation, because I am only giving an idealization, because you have a soft spot on the blade about which you want the blade to flex in a hingeless blade. Okay. Now, whether your pitch angle, whatever the pilot gives, does he give inboard of this or outboard of this? Okay. If he changes the pitch angle outboard of that, that means the spring assembly is not rotating, because this is lag spring, this is flap spring. But suppose you go and change the spring assembly, if your pitch angle of the blade is changed inboard, inboard means inside this, then what will happen? When you change the pitch angle, the spring also is going to rotate. So, when you have a pitch, your spring assembly can come like this, and this is my hub, and this is my theta control or theta pitch angle, whatever it may be. Spring is changed and my blade may be coming out like this. That means I am having my pitch bearing inboard of this. So, what is flap? Flap is rotation about y axis, lead lag rotation about z axis. Now, when I rotate, the spring assembly is now inclined. Okay. Because of this, if I make one rotation, you make now flap and lag are small angles you take, whereas theta control it can be 10, 15 degrees you can go. So, this you take it as slightly large, no problem, but flap you take small angle and assume that it is a vector. Small angle you can treat it as a vector, not large angles. You give if you say flap that is flap down, I call it beta, or if I want flap up, I can put beta that side, but the sign convention will get a little goofed. In the sense, this is counterclockwise rotation, the blade is here, if I do flap in, this blade is coming down, even though this is the plane of rotation. But if I want to use the helicopter convention, flap up must be positive, then this will be other way around. And lead lag counterclockwise rotation, this you may give zeta, this is the lead lag. Okay. Now, if I have these two, you have to find out what is the flap moment, what is the lead lag moment. That is, you can say applied external moment, because the blade is going down means you put some moment about this. So, you may call it My and Mz. Okay. You can have this as one convention, but you will find because when I did this in the 80s means beginning 80s, we were discussing lot of this, how do you get that spring, then what, different people had different, but this is one simple assembly, you have more complicated assembly also. That means you introduce hub stiffness also, not only blade stiffness, put hub stiffness. Okay. That means you will have two sets of assembly of springs, one hub which does not rotate, another blade which is rotating like this. Now, you get an equivalent spring for that entire assembly. Okay. That is there in my NASA report. I will not go into all the formulation, but this one simply explain. But here, please note, this is the flap down, I am taking positive, counterclockwise rotation, here counterclockwise rotation. You know, there is a lot of confusion, because flap is up, you know, what should I do, how do I take it. Finally, if you take this way, you will get one set of equation which is consistent. But then you want to introduce beta, I want beta up is positive, means you have to change the symbol, sign of beta. When you do that, then you will get one set of equations. So, different people have used different, only thing is depending on how they define this beta. If you follow this as a conventional counterclockwise rotation is positive, you will get one very systematically, absolutely no problem, that I will write it. I will write the stiffness, but you will find in different reports it may be given in different format. Okay. So, you should not think that this is right or that is right. If you follow what assumption he has used, then you will find that everything will be fine. So, I am just using this convention, applied moment My Mz. Because of that, the blade is down and it is rotating. So, both flap, lag. This is purely structural coupling, because my pitch bearing is inboard of the spring assembly. Okay. Now, if I have, I am putting in a matrix form K, I call this as, this is the flap spring K beta, this is the lead lag spring which is K zeta. Okay. So, K beta cosine square theta plus, if you are interested, you try, you derive yourself, it is not very difficult. because I want to discuss this cosine theta. K beta sine square theta multiplied by beta zeta. This equation corresponds to this, okay, whatever this relation, okay. This relation corresponds to this. It depends on how they, this is the applied moment, okay. Applied moment my mz, okay. Flap moment, lag moment, but downward, please understand. So, the convention everything you have to be very careful. Now, in the NASA report what I used was I used minus beta, okay, and then I get the not a applied moment, I used the restoring moment. So, I put one more minus sign. So, you will find that there will be some sign difference between this and there, and some other research paper you will find there will be some other sign, but you have to be careful that what sign he has used for everything, okay. Finally, all will come out to be correct equation. Only thing is do not take it as though this is following that convention, okay. If you modify the convention and apply restoring moment, this is the applied moment. Restoring moment means what the spring gives on the blade, okay. This is what externally you apply on the spring. You can take what is the spring load that comes onto the blade, then you will put a minus sign, okay. And then if you say beta, I want to define flap up is positive, means I put a minus beta, okay. Then what will happen is some of the terms here change sign, okay. That is just for information I am giving. If you want, I can write the other expression also, restoring moment with the minus beta, okay. I will put this is applied moment with that. Now, I am saying restoring moment, that means the spring moment with flap up positive, okay, with the flap up positive. That means this is flap down is positive. If you want, I can write flap down positive here because of my convention, okay. Here if I write this is my mz, this will become k beta cosine square theta plus theta, but you will have a minus sign here, k beta sin theta cos theta, and this will be same. This is k beta sin theta cosine theta, and this will be minus sign again, minus of k zeta cosine square theta plus k beta beta zeta. In this case, beta positive flap up, in this case beta positive flap down. This is external moment, this is the restoring moment. Basically what you do is, if you want applied moment to spring moment, you put a minus sign, everything minus, 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 okay. And then you change wherever beta is there, that sign will change. So, this minus, 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 this will become plus, plus, but these two will stay as minus. Okay? That is all. This is just the sign convention. But what I want to discuss here is, this is very interesting discussion. You have, if I introduce pitch bearing inboard of flap and lag hinges, I introduce flap lag coupling, and all the hingeless blades, because hingeless blade you have here, pitch bearing is inboard, you change the pitch here, coupling is always there, you can't avoid. Now, how much coupling comes? This is again, see, lot of debate. One is, what they did was, whether whatever pitch angle I give, whether the same pitch angle goes to the spring also. I can have, okay, if it is, if I rotate by theta, the spring assembly rotates by r theta, where r is less than 1. That means, I give a pitch angle of theta, but the spring assembly does not rotate through same angle, but it rotates slightly less than that. So, that is the coupling. What they did was, they put a r, parameter r. So, theta is r times theta control. This r can be from 0 to 1. 0 means pitch bearing is outboard. Okay. So, wherever theta is there, you put theta. If r is 1, this is directly theta control, pitch bearing is inboard. But if it is in between some value, because it does not, there could be a slight deformation, okay, because it is a structure. I give a rotation, it need not go faithfully, full rotation need not go, there can be a slight decrease. So, this interesting thing, what happened is, if you look at the coupling term, suppose I have only flap motion, I do not have lead lag, then automatically I get a lead lag moment, okay. I get a lead lag moment because of this. Now, if I do not want coupling, one is you take the r is 0, that means pitch bearing outboard of the spring assembly, that means the spring will not, there is no coupling between flap and lag structurally. But if you introduce k beta equals k zeta, that means the flap stiffness is same as lag stiffness, that is structural stiffness, that spring assembly, then I do not have any coupling. No matter what, I can have the rotation, okay, whether pitch bearing is inboard, pitch bearing is outboard, does not matter. Now, this, whether you can design a blade, okay, this is called matched stiffness blade configuration. That flap stiffness, but please understand, I am deriving all these things with this type of idealized model. Elastic blade, you have to see at the junction where the stiffness is there, where it is the flexure, you have to see whether you can get matched stiffness. Usually it is difficult, okay. But please note, experiments were carried out to study the effect of these, and I will bring that there. You will find data will, results will just change, the damping data, because I am not gone into aeroelastic stability part, but these parameters have tremendous influence, okay, on the damping, structural coupling, flap lag. But now you realize elastic blade, hingeless blade if I take, I can't avoid this coupling, because by construction I am getting that, and pitch bearing is inboard. Now you say I do not want stiffness, then can I make the blade at the point where it is both the flap stiffness, lag stiffness must be same. That means it should be a square section with the same distribution of material at the point where it is flexing. If I can design, this coupling is removed. Okay. Yeah, isotropic, no, dimension. See, dimension also equally matter. See, suppose you take isotropic, you take a straight edge ruler, you can bend one way easily, other way you can't bend it. That is the yeah. But the stiffness part, I am representing the flexural stiffness by a spring. See, the blade is not going to bend, you are putting at some place where you deliberately make it a little soft. Yesterday he was mentioning that, so that you create, but the stress levels, the strain levels are below the limit, but still it is flexing. Okay. At that location you make these two stiffness same, then you can eliminate the flap lag coupling. But the flap lag coupling is not most normally lag stiffness is high, lead lag stiffness is much higher, okay, than flap stiffness in the design of the blade. But you find you try to reduce, but this coupling will affect. Now you know automatically I can't analyze only flap motion, okay, because the moment I have flap I get a lag movement will make the blade go lead lag, and if I have any pitch associated with that, then that will create a problem, and then lead lag motion will come and give me a flap deformation, okay, because these two are coupled. Lead lag if I have, I will get a coupling to lag. So, flap and lag motion cannot be decoupled. All along we were, the full course till now, only flap motion we were concentrating, only flap. We never bothered about lead lag motion. Actually, as a subject or the dynamics of the helicopter, if you look at it, flap is very important, but lead lag creates more problems, okay, but you cannot avoid. So, you have to consider lead lag. Lead lag will come into the picture. Then of course, elastic torsion. So, that is why flap, lag, torsion, that treatment is the full dynamics, okay. And all these things started from the 70s. People try to understand what is really going on in the flap lag. Those days it is a rigid blade with this type of spring assembly only. All research papers, if you look at it, even 80s, yes. But now elastic blade models have come, okay. Now I will just, that is the matched stiffness configuration which can eliminate the structural flap lag coupling, okay. So, I just show here the diagram with whatever I have written there with the, because here I put a minus sign, you see, that is the restoring moment with the flap up positive, that is slightly modified. When the blade pitch is theta, spring assembly rotates through r theta. So, I put r. So, experimental setup was made, coincident flap lag springs, so that the blade is made rigid, and they rotated and then studied the, and then the data was given for correlation, okay. So, those data I am I do not know whether I have for some problems, but not for all the cases. Okay. The other case which I want to tell you how the flap lag coupling will come is because of this. This picture I do not know whether, see, I will show this diagram. This is a bit messier, taken from some reference from, you see, this is the original blade, this is the deflection, this is the deflection, okay, up, down, the dashed line. Now, lag forces will try to give a pitching moment, okay, lead lag forces. Similarly, when the blade goes down, that lead lag force will give a pitching moment. That depends on how much it has flapped. Okay, so how much you flap, and that becomes a factor with the lead lag force, that is the drag force in changing the pitch angle. Similarly, how much the blade has gone back and how much is the lift, that will give a pitching. This is an elastic blade, that is why then it will give. So, if you do not take these things properly, your control rod loads, everything will be wrong. So, I will tell you, this is structural part, aerodynamic part is another. So, usually predicting control rod load is always tougher. Okay. You really do not know, because the elastic blade, now you take more modes into account, whether this is really happening, get all the moments properly and then transfer them. And so, this is just a picture showing how one load will affect based on the deformation in another mode to something else, pitch angle. So, you see flap deformation, lag load affecting pitch angle. Similarly, lag deformation, flap load influencing pitch angle. Now, you see, if you want to analyze the problem, you can't neglect anything. You have to have flap, lag, torsion problem, okay, which is very complicated. So, we are not going to do that in the course, but this is just a introduction to you to see the complexity in the factor of safety for what? Factor of safety. See, it's all, see, sometimes I can only say what little I know, because factor of safety is always it should have infinite life, that is the design usually. But how much load you are getting in the pitch link is very difficult to predict. Sometimes the error can be of the order of 200-300%, okay, particularly pitch link load. So, you design by experience, so you learn now what is that load, after that you monitor pitch link load and then you may replace it after so many hours. But once the flight, that is why initial design you do based on theoretical calculations, and theoretical calculations, if you are a beginner, okay, nobody is assisting you, nobody has made anything, but you have to take a risk. You put a pitch link, you fly it, you measure it, you see, oh, it is not failing, then you make it bigger, then you will find, okay, this is good. After that only you go back, oh, this much is the load that is coming, where is it coming from, how it is coming from, okay. But I do not know, normally pitch link, maybe they will have safe life, I do not think they will have infinite life, I do not know, maybe he will be able to tell you. Safe life means you operate it for so many hours, after that even if it looks good, remove it, put a new one, okay. Is that safe life, right? That's all. You do not take risk in those things, because what you do not know, you have a safe approach, okay, towards those problems. Okay, now I will introduce to you the lead lag dynamics. Okay. Now, please whether should I derive the equations, that you have to tell me. If you want to derive, that will go into full derivation. Okay. Again, position vector, velocity, acceleration, then inertia moment, and write it. But I won't write any aerodynamic moment for this, because that is a separate expression which you have to give, because that is a drag load. Okay. I will just briefly tell you the lead lag dynamics. So, this is isolated in the sense only lag motion. I do not have any flap motion, nothing. Please understand, like what all we derived earlier, it is only flap motion. Now, I am saying, hey, there is only lead lag motion. Okay. So, you put a spring with a hinge offset, all right. Now, like you have flap frequency, natural frequency, rotating flap natural frequency, you will have rotating lag natural frequency, because this is a dynamic system. But what is that value? Okay. If you derive the equation of motion for this, please understand, this is I am giving a deformation zeta, the blade is hinged about this point, and there is a root spring which is k sub zeta, which is, so the motion is in the plane of the diagram. Okay, it just, so when it goes rotates, the blade can move back and forth. Okay, this is the equilibrium position. Now, if you write the dynamics for this, the equation will be like this. That is what you can derive it. If you want the derivation, I will start next class, not today. Okay. If you want the derivation, right, this is my inertia. Of course, there is another term which is inertia, mxcg, you know the definition, integral m x dx, m is mass per unit length. Okay. So, here IB, we know that it is integral 0 to r minus e m x square dx, and m x m is mass per unit length. So, if you have uniform mass, uniform mass, you will have IB is m r minus 3, because I am just writing it what I wrote last class, and mxcg becomes m. Okay. This for uniform mass. So, if I substitute for uniform mass case, I divide by IB, convert it into non-dimensional time. This is my lead lag rotating natural frequency. So, I will put it omega bar RL is k zeta over IB omega square plus, if you want to put it as 3 by 2 E bar by L bar, that is one form, that is uniform, or else mxcg E over IB. Okay. Both are fine. And this is power half. Okay. This is my rotating lag. If you, just for comparison, if you take rotating, what we got, flap, you had 1 plus okay, this is flap. You see, this is flap frequency, you will have 1 plus, and of course, I do not have all the pitch flap coupling. If I put pitch flap coupling, that term will come. Okay. The one is missing here, that is not there, that is all. Now, because of this, you find that suppose k zeta is 0, that is there is no spring, it is a articulated blade. Lead lag frequency rotating depends on what is the hinge offset, and in MXCG or RL this whole term can be replaced as, if it is a uniform mass, it will be 3 by 2 E over R minus E, or you can write it as 3 by 2 E bar L bar. E bar is E over R, okay, and 1 minus E bar is L bar, and that is what is written there. If this is 0, this is the value, and hinge offset usually you will have about 4%, 5%, but sometimes it may go to 10%, okay, hinge offset. So, the lag frequency non-dimensional, it is not very large, it is usually of the order of, I have given here, it is about, for articulated blade, it is in the range 0.25 to 0.3, 0.25 to 0.3, whereas flap is 1 point something, okay. And hingeless blade, because articulated blade there is no spring, it is just a hinge. So, you get a hinge offset with this, that means this term is 0, you can find out what is the corresponding hinge offset. So, immediately you can calculate what is the rotating lag natural frequency. But if it is a hingeless blade, usually it goes to around 0.7, okay. Now, there is one more terminology which is there. This is hingeless blade, I said 0.7, but can I have greater than 1? Yes, you can have greater than 1 provided you do this, stiffness you increase, and suppose another part is this omega, if it is small, that is the rotor RPM. When you are starting the blade, RPM is low. When you go to the operational 100% RPM, it will have a much higher value. That means my lead lag frequency, I am changing it. As my omega changes, then non-dimensional number itself is changing if I have a stiffness, okay. Is it clear? Because as I change my omega, lag frequency is changing. So, this is the terminology. If omega bar rotating lag is less than 1, this is called soft in plane blade, okay. This is the terminology. If it is greater than 1, it is called stiff in plane blade, okay. Soft in plane, stiff in plane, and at the operating RPM. Suppose you operate at say like our blade, we operate at 1500 RPM, small one, big rotor 300, 400, something like that. If your lead lag frequency is greater than 1, then it is called a stiff in plane blade. If it is less than 1, it is soft in plane. Now, how do you fix which blade which soft in plane blade or stiff in plane blade? But the same blade, if I increase my RPM, what is originally stiff in plane will become a soft in plane, okay. So, it is really dependent on the operating RPM, but at the operating RPM, which I should choose. Okay.